Okay, so let's write down what the actual updates were. They were C0 becomes A10 transpose times B0 times B1 plus C0, and C1 becomes A10 times B0 plus A11 times B1 plus C1. Now, I like to break this up. And the way I like to break this up is, instead of writing this as one step, I like writing it as two steps, because actually in practice that's how you would implement it. You would actually do a library call to do this matrix multiply, and then this matrix multiply, and finally this one. So I'm going to take this and say, oh, I can break this into two steps. I can first add this to C1, and then I can add this to C1. Okay, and these two steps together have the same effect as what we did before. Okay, now let's go over here and let's think about this. Okay? What pieces of the matrix do we actually work with? We work with this right here, and we work with this right here in B. That's part of our first matrix multiply. And then we again use this, but then we use that matrix there, etc. So we're using different pieces of matrices A, B, and C. Let's build a little bit better picture here. At a typical point, we have our matrix C partitioned like this, where this is C0, C1, C2. Being updated by, I'll do a plus equals so I don't have to write matrix C again. A matrix like that, which is our matrix A. Remember, it's symmetric, so you can think of that like that. And then matrix B partitioned like that. Now, as a general rule, these matrices are huge. The block size you pick here is relatively small. So think of a matrix that's, say, 5,000 by 5,000, and this little panel here might only consist of 100 rows. Okay, which means that this little block in the middle might be 100 by 100. And that's going to turn out to be important. So now what happens? If you look at this particular operation, it equals this transposed times that. Okay, so this, let's take this piece and let's take it over here but transpose it, and then it would look something like that, wouldn't it? Let's write C down first. So we have a block of C, C0, that we're updating with that panel of A transposed, which is why it's a long narrow panel like that, times a row panel of B, B1 right here. This is A10 transpose, this is B1, this is C0. Okay, and what do we recognize here? It's a matrix multiply with a matrix where this is relatively small. Now remember, our matrix A was typically m by k, and matrix B was k by n. And so what we're really saying here is that the k dimension of what we compute with here is relatively small. And that's an important enough special case of matrix multiply that we call this a rank k update. Where have we seen something like that before? We saw a rank 1 update before. Well, that's obviously the special case where this block only has one column and one row. Okay, so that is a matrix multiply. Right? if we have a really fast implementation of matrix multiply, then this part of the computation will presumably execute very rapidly. That's good. What about this part right here? Let me just erase this to create some other. Okay, so here we have the block A10. That's again this block right here. Oh, first of all, we have block C1. That's this narrow block here, row panel, being updated with a panel of A. So this again, a few rows, say 100 by thousands maybe, times matrix B0, but B0 is now a relatively large block. And this is A10, and this is B0. What is that? That's a matrix multiply, but for the special case where this row dimension of A is relatively small. It's a different shape of matrix multiply. If matrix multiply can achieve high performance, then this would achieve high performance, this subproblem. Okay? Now let's go on to this part. That is also this long, narrow block of C1 being updated now with a small block of A, that block on the diagonal, times a block of B. Okay? Now, first of all, if these blocks are large and this is small, then you can argue that most of your computation is going to be in these two operations, and therefore if these two operations can attain really good performance, then that's really what you care about, because relatively little of your total computation is with this operation right here. And you can calculate exactly how much computation is with each, but that's a little bit beyond this course. What you notice is that this matrix itself is actually symmetric. Why? Because it's a square block on the diagonal where this block is square and that block is square as well. So really here you can't just call a fast matrix multiply, you would have to call a fast symmetric times matrix multiply, updating a matrix. Wait a minute. We're coming up with algorithms for doing exactly that, and now we're saying, but we need to do it as part of that as well. Well, remember, how efficiently that gets computed is not all that important, because we're saying most of our computation is in these other operations. So we could use, for example, an unblocked algorithm there. Unblocked algorithms turn out not to get quite as good performance. We'll talk about that in the enrichment. But we don't care because we don't spend all that much of our time there anyway. Okay. Or you could simply take this little block, copy it over so that it just becomes a general square matrix that happens to be symmetric, where you actually copy the lower triangular part into the upper triangular part, and then call a regular matrix multiply and get it done that way. In general, you don't want to do that because your matrix A may be really large and then you would need twice as much storage, etc., etc. But for a smaller block of it, this might be okay. Okay? Anyway, what we have just demonstrated is how a symmetric matrix multiply can be decomposed into other matrix multiplies that are just regular matrix multiplies. And therefore you can cast most of your computation for this operation in terms of a matrix multiply. And if that's the only operation that somebody out there has highly optimized for whatever computer you happen to be on, you'll be okay.